This video will focus on the learning targets. I can describe the dissolving process for ionic versus covalent compounds, and I can explain what factors change dissolving rates and the solubility of solute. Honestly, of all the videos I've done, just realized that this is kind of less topicy than other ones. It's a hodgepodge of things you need to know about solutions in order to make solutions understandable, and I felt like it was the most effective thing to have as a video for you guys when you need to look back and learn some of the harder topics. So step one, what is dissolving? Dissolving requires two processes. So essentially, number one, you have to break the thing you're dissolving down to microscopic components so you can't see them anymore. But then step two, you have to replace whatever attraction you broke in order to dissolve with new attractions. So these two steps are usually called dissociation and hydration. Dissociation, which is the first step, is the breaking apart of whatever current force is holding the structure together. So if you're dissolving an ionic compound into water, then I'm going to break apart that ionic compounds to separate the ions into separate components like Na plus and Cl minus. If instead I'm dissolving a covalent compound, then I'm going to be breaking apart whatever IMFs they currently have. So step one is that process of breaking apart the current force of attraction, so that electrostatic force of attraction, either potentially an IMF or an ionic attraction, so that the components get so tiny you can't see them. Step two then is to replace that force of attraction with a new force of attraction. So for an ionic compound getting dissolved, we would replace it with an ion dipole with whatever polar thing it's being dissolved into. If you're dissolving a covalent compound then into another covalent compound, we would just replace the IMF with a new IMF. So in many ways, I think of dissolving as a break and make. Step one, I need to break apart what's currently there by putting energy in. Step two, I then make a new attraction as I release energy. And we'll talk more about energy when we do thermo. The other thing I want you to be aware is when we talk about solutions, we're mostly going to be focusing on like a solid dissolving into water because that's kind of the universal solvent. It's polar, it has charge, it's really good at dissolving ionic things and polar things. But there are tons of solutions even in your lives that don't fit the category of like a solid dissolving into water. Okay, for example, air. Air is considered a nonpolar solution, lots of nonpolar gases all dissolved into each other. Humid air would be like that liquid and gas. Okay, gas into a liquid, carbonated beverage. So anytime we talk about a gas dissolving into a liquid, you just have to think about pop. Liquids with liquids, so anytime you buy a solution in the store like vinegar or isopropyl alcohol, those have all been diluted, so they are a liquid solute with water solvent. And then you can even have like solid solutions. So sterling silver is an example of a solid solution, or most alloys are an example of solid solution. So solution isn't phase specific as long as we have those two processes of dissociation and hydration happening. It doesn't matter what phases we're in. Now, once you're dealing with a compound that can dissolve, the next thing to think about is how much can I dissolve? So there's a term called solubility, and the problem with this term is we're not used to using it correctly. Usually when we talk about solubility, we talk about like, oh, the ability to dissolve. But it turns out the word solubility is actually a measurement. So solubility refers to the numeric number of the max amount of solute that can dissolve into a solvent. Okay? So you can't dissolve forever. Essentially, there's a maximum. If you're putting Kool-Aid into the water, eventually it will get to a point where you can't put any more Kool-Aid into the water. The reason there is a max is because you need to be able to do the dissociation and hydration. Okay, part of why the compounds are falling apart in the first place is that charge attraction to whatever is the background solute or solvent, and the proportions in terms of how much can dissolve, it is chemical dependent. So you can dissolve a lot of salt and sugar into water, but you can't dissolve as much of like a specific ionic compound into water. Now, concept-wise, we still can talk about like, will it dissolve, won't it dissolve? So soluble things will have a solubility because they did dissolve, where if you have unsoluble things, it means they don't dissolve. There are two more words that are kind of weird, you just have to be aware that they exist, which is miscible and immiscible. Miscible is used when you have a liquid solute. So if I'm dissolving, again, isopropyl alcohol into water or the acetic acid for vinegar into water, those are miscible. So immiscible would be a liquid solute not dissolving into a liquid solvent. So like oil and water, they are immiscible, not technically insoluble. So we're going to be dealing with solubility curves. We're actually be doing a lab where we create our own solubility curve. And what you have on here is each of these lines is a different ionic compound, and what these are the solubility for that compound. So the numeric max amount that can dissolve into 100 grams of water. So one thing we see here is solubility is substance dependent and temperature dependent. So as I heat up, my solubility generally increases. Okay, so the way you read these essentially is just find a spot on a line and the corresponding temperature and substance. So like for KCl at about 40 degrees, about 40 grams dissolves. Where like for KNO3 at 40 degrees, we have about like 62 grams dissolving. So it's all how many grams per 100 grams of water. You can see that on the y-axis, and that is your solubility. So that's your maximum that can be dissolved, is what the line corresponds to. So those are the last few terms I want you to be aware of: the saturated, unsaturated, supersaturated. So saturated corresponds with solubility, in that if you are at your solubility number, you are saturated. You cannot dissolve any more. If you put more in, it'll just fall to the bottom and sit there. Unsaturated just means then we're less than the max, which means we could put more in and it would dissolve. Supersaturated is a really specific scenario I'll show you in class, where you can dissolve more than you should, cool it down, and it doesn't undissolve. It's very unique and very specific. Going back to these graphs then, again, for KCl at 40 degrees, if you put only 20 grams in, you would be unsaturated because all 20 grams would dissolve. You could fit more. So at 40 degrees for KCl, if you put 40 in, you would be saturated. You couldn't fit any more. And so if you try to put like 50 grams in at 40 degrees, you would just have 10 grams that just kind of hung out on the bottom, and that no matter what you do would just never dissolve. So anything beyond the saturation point for most compounds just won't dissolve. It'll stay a solid crystal on the bottom. That's it for your general introductory kind of pieces for solution. Go ahead and try the quiz and have a nice night.